Okay, this is exercise 6.2a, question 8. Points A, B, and D have these position vectors here. And for part A, we're told that AB is equal to DC. And so it says find the position vector of C. Okay, so first of all, let's write these things out. So OA has vector 2, 3, 1. And OB is the vector -3, 28, 16. And OD is this vector, 5, 21, 7. Okay, so for part A, we have that AB is equal to DC. Of course, AB is equal to OB minus OA. So that would be -3 minus 2 is -5. 28 minus 3 is 25. And 16 minus 1 is 15. Okay, and for now, let's say that OC is C1, C2, C3, so that we can write OD minus OC as the vector DC. Sorry, it should be OC minus OD. So C1 minus 5 and C2 minus 21 and C3 minus 7. Alright, so that is OC minus OD, which is the vector DC. And so clearly, so C1 minus 5 equals -5, so C1 is equal to 0. C2 minus 21 is equal to 25. So that would mean that C2 is equal to 46. And then C3 minus 7 is 15, so C3 is equal to 22. Alright, moving on to part B now. So we found our position vector OC, so we've answered A. Okay, part B says that the line L passes through A and B. Alright, so since L goes through A and B, clearly it has the direction vector AB. So one way to write the equation for L, so let's just label this first. So the vector equation for L can be OA plus T times AB. So 2, 3, 1 plus T times the vector AB, -5, 25, and 15. Meanwhile, we have this plane pi that has Cartesian equation 2x plus y minus z equals 6. 2x plus y minus z equals 6. And we want to show that the line L lies on pi. So all the points on this line are also contained in this plane. Well, that's not a problem. We can just call this arbitrary x, y, and z. And to show that a line lies inside a plane, it just has to intersect at 2 points. If it intercepts at 2 points inside the plane, then that means all of the points on the line have to be inside the plane. So we can just take any 2 points on the line and show that they're in the plane. And we do that by showing that they obey this equation here. So let's say t equals 0. So we know that 2, 3, 1 is on L. And we also have that 2 times 2 plus 3 minus 1 is indeed equal to 6. So 2, 3, 1 is also in pi. And this time we can take t equal to 1. So if t equals 1, then we get the points 2 minus 5 is -3, and 3 plus 25 is 28, and 1 plus 15 is 16. So this point is on L. And we can check if it's in pi by seeing whether it obeys this Cartesian equation here. 2 times -3 plus 28 minus 16 does indeed equal 6. So it is negative 3, 28, 16 is also in pi. So since our line L intercepts the plane at 2 points, it must be the case that the line is completely contained within the plane. Alright, moving on to part C. It says find the coordinates of E. Point E is some point on L, by the way. So find the coordinates of E such that the line segment ED is normal to pi. So in other words, ED is some multiple of the normal vector of pi. Let me write some of these details down. Okay, part C. So we have the normal vector of pi, or at least a normal vector, is 2, 1, negative 1. Okay, we got this vector OE, which is apparently on the line L. So we know that OE is equal to 2, 3, 1 plus t, negative 5, 25, 15. Already forgot the numbers. Negative 5, 25, 15. For some value of t. Okay, and we want ED to equal Kn. Want ED equals K times N for some number K. Not a problem. ED is equal to OD minus OE. OD was 521.7. Okay, minus OE, which is 2 minus 5t, 3 plus 25t, and 1 plus 15t. Okay, so 5 minus 2 is 3, and then so 3 plus 5t. Okay, 21 minus 3, so that will be 18. Yeah, 18. So 18 and then minus 25t. And then 7 minus 1 is 6. Minus 15t. Alright, so that's our vector ED. And what we would really like is for this vector to equal k times 2, 1, negative 1. Let's see if all our dreams can come true here. So we got 3 plus 5t is equal to 2k, according to these first coordinates. And then the second coordinate, 18 minus 25t, is equal to k. Okay, so then that means that 2k is actually equal to 36 minus 50t, and so we get that 55t is equal to 33, and so it must be the case that t is equal to 33 over 55, which I believe is the same as 3 over 11. No, that's not right. 3 over 5. And then so we would have, according to that, subbing in t equals 3 over 5 here, we'd have 3 plus 3 equals 2 times k. So that would mean that k has to equal 3. And then the only question is, do we have the last coordinates satisfied? So in other words, we would need 6 minus 15t equals negative k. So 6 minus 15 times 3 divided by 5 equals, so that would be negative 3, which does indeed equal negative k. So we're good. And let's go back and check what the question was actually asking for. Find the coordinates of E. No problem. We already have that OE is well, this vector here. So it's 2 minus 3/5 times 5. So that would be 2 minus 3, which is -1. And we have 3 plus, so 3/5 of 25 is 15. So this one will be 18. And then this last one is 1 plus 3/5 of 15, which is 1 plus 9, which is 10. Alright, so that's our OE coordinate. Alright, lastly for part D, it says find the area of the parallelogram ABCD. Now just a reminder of what we already know about this parallelogram. So we know that AB is the same vector as DC. And so we can quickly get the area of this parallelogram by using the cross product, because earlier we showed that the length of the vector that is AD crossed with AB here, that's equal to the area of the parallelogram. So let's call this parallelogram P, area of P. So we just need to find the vector AD cross AB and then calculate its length, and that will give us the area of our parallelogram here. Alright, so I just wrote out some of the details so I don't have to keep going back and forth. So the vector AD is, of course, the vector OD minus OA, and then we already calculated AB before. And we're looking for AD cross AB. So let's go ahead and calculate that. So this is 3, 18, 6 crossed with -5, 25, 15. Okay, so the first entry, we delete the first row. So it's 18 times 15 minus 25 times 6, which is 120 according to my calculator. And then for the second one, we delete the second row, and then we do the determinant backwards. So -5 times 6 minus 3 times 15. And even I can do that one without a calculator, hopefully. -5 times 6 is -30, minus 3 times 15 is 45. So I believe that makes -75. And then lastly, we delete the last row. It's 3 times 25 minus -5 times 18, and that is apparently 165. Okay, so that is our AD cross AB vector. Beautiful. To find the area of our parallelogram, we just need to calculate the length of it. So the length of AD crossed with AB is equal to the square root of 120 squared plus 75 squared plus 165 squared, and that is 15 times the square root of 210, or 217 to 3 significant figures. And that completes part D of the question, because that must also be the area of our parallelogram.